Meet Hank. He's not just any technician. He's the guy who gets it done. Fast, efficient, accurate, but only because he's got the right tools in his hands. Evergreen telemetry gives HVAC pros like Hank the ultimate advantage. No more guesswork, no more wasted time. Just fast, reliable wireless airflow measurements so you can move on to the next job.
When airflow's tough and time is tight, Evergreen telemetry makes it right. With tools so smart, so easy to use, we'll help you when you've got nothing to lose. Faster, safer, smarter too. Evergreen telemetry's here for you. From homes to labs and enterprise halls, we've got the tools to do it all.
Good afternoon, everyone. I'm Sim with AABC, and I'd like to welcome you to today's Tap Talk webinar and thank our sponsors, Evergreen Telemetry, for sponsoring this session. Just a few housekeeping items before we get started. Our presenter will be holding the questions until the end of the presentation, but we encourage you to submit them at any given time using the Q&A button. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists so that our producer, William, can assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to the web emails within 24 hours. And finally, if you are a certified TBE or TBT, your CEUs for attending this webinar will be automatically uploaded to your respective portal after the webinar. Today's webinar is fundamental of heat transfer and humidity control. So let's go ahead and welcome today's speaker, that's Justin Lewis. Justin is an AABC TBE and CXA with more than 25 years of experience in the construction industry and the owner of Pangea Consulting Group. With a passion for tab and commissioning, he is dedicated to the continued improvement of the construction process. Through years of experience and lessons learned, Justin offers insight and strategies for more effective project management. Without further ado, I'd like to hand it off to Justin to kick us off. Justin, can you go ahead and take control of the screen, please? I believe it's on mute because we cannot hear you, Justin.
Clarify concepts regarding heat transfer and humidity. It's also intended to provide inspiration and for professionals who may be looking for strategies and techniques for training and mentoring new technicians. Years ago, when I was coming up, there weren't a lot of resources when I was transitioning into a certified technician and later up there getting my stamp. I got a lot of regurgitation of formulas and definitions, which helped with passing the test. But the key transition point for me was when I really started to understand the engineering concepts. That allowed me to troubleshoot properly and understand the intent of the design. And it's a key transition point for all technicians. Albert Einstein is credited with saying, if you can't explain it simply, you don't understand it. Now, this simple quote is profound and has sat with me for over the years. As I've become a mentor myself, I've always thought about this and wanted to make sure that I can explain things properly, and I hope this presentation lives up to that expectation. The first thing we need to understand is the term heat transfer. When we're talking about heat transfer, we're ultimately talking about energy transfer. We need to understand the difference between energy, temperature, and heat. Energy is the measure of something's ability to do work or produce heat. Energy is not a substance. It cannot be seen or touched. Rather, it is a property of the system and is considered abstract. It's a measurable ability or impact of physical systems, much like velocity is. Think of water running through a pipe. If it's running through the pipe, you can measure the velocity, but if the water stops moving, there is no velocity. It does not exist in that condition. However, the water still exists. There's several classifications of energy. First is thermal energy. Thermal energy is the energy that comes from the movement of particles in a substance. The faster a particle moves and the more thermal energy it has, it's what we experience as heat and is transferred through conduction, convection, and radiation, which we'll talk about more in a couple minutes here. There's kinetic energy. Kinetic energy is an energy an object has due to its motion. The faster and heavier an object is, the more kinetic energy it has. The key point to this is that the mass of a particle plays as much of a role as the velocity. That's why water transfers heat more efficiently than air, because the molecules are denser and have more mass, meaning that they store and transfer more kinetic energy when they collide with other particles. There is electromagnetic energy. This is the energy that travels in waves and can move through space. It includes radio waves, microwaves, visible light. Radiant heat transfer is reliant on these waves. There's chemical energy. Chemical energy is stored energy in the bonds of an atom. It's released or absorbed during chemical changes and reactions, such as food digesting, burning fuel, or battery operation. Note that this process relies on a change in a substance's chemical compounds, not to be confused with latent heat due to phase change, which we'll cover later in the presentation. And finally, there's potential energy. Potential energy is energy based on the position or configuration of a substance. For example, a boulder on top of a hill has no energy because it's not moving, but it has the potential for energy if it was to roll down the hill. Now we have defined energy. Let's talk a little bit about temperature. Temperature is the measure of the average kinetic energy of the particles in a substance or system. Temperature does not represent the total energy in a system, only the average motion of particles. If we have a cup of hot water at 160 degrees and a swimming pool in the backyard full of 70-degree water, the cup of hot water would have a lower total energy, even though it has a higher temperature, because there's more particles in the pool, there's more total energy. But the average temperature or the average movement of the particles in the cup are higher. Let's look at how this works. So if this is a system and we have particles, the particles start, as they start moving and bouncing around, what we're looking at is, what is the average of these particles? Heat energy temperature. Heat is the degree of hotness or coldness measured on a defined scale. Heat is commonly measured in Fahrenheit and Rankine in the US standard. Fahrenheit being our normal measuring system. Rankine is in reference to absolute temperature. In the metric, we have Celsius, Kelvin. Absolute temperature refers to the temperature measured from absolute zero. Absolute zero is the point at which a system is in a state of its lowest possible energy. Molecules in this system would have zero movement. The temperature scale based on absolute zero as a starting point are Kelvin and Rankine. As these temperature scales are somewhat extreme for reference of temperature ranges we see and experience here on Earth, we have Celsius and Fahrenheit for our everyday use. So with an understanding of energy and temperature, we need to understand the concept of energy transfer. So if we look at two systems and we break these two systems apart, we'll see that the system on the left represents a system with high energy, and the system on the right represents a system with low energy. As they come together, the particles start colliding and transferring that energy, and they will find themselves into a state of equilibrium. This process is called heat transfer. Heat is the measure of energy transfer from one system to another. Heat is the amount of energy transferred in a process, excluding any thermodynamic work or the transfer of matter. Thermal energy can be transferred between matter by one of three processes: conduction, convection, and radiation, or radiant. This concept is often represented by a pot of boiling water on the stove. But for now, let's imagine that the water is heating up and not yet boiling. Several things are happening as the burner is turned on. We have heat transfer, we have heat flow. Now, the difference is a cup of coffee. If you pour creamer into it, you're adding two systems to each other. One's cold, one's hot. As you pour them together, they're going to find equilibrium. Now, with a pot of boiling water, we have a constant source of heat being generated. So where there's heat transfer, there's also heat flow. So we don't see when we introduce cold water and warmer water, we don't see them quite equalize out. We see the heat continue to transfer from the flames into the pot of water, and it heats the water completely. That's heat flow versus heat transfer. But let's get back to the three processes of thermal energy transfer. We have conduction. Conduction is the process of energy transfer through direct transmission. Heat or electricity even will transfer through a substance when there's a difference in temperature between the two adjoining regions. Energy is always trying to reach a neutral natural state. It's trying to reach an equilibrium. So when two systems come together and one system has a lot of kinetic energy and one system does not, those particles will ultimately try to transfer those and come to an equal, neutral, natural state. We can see conduction process heating of the metal spoon. As the handle gets hot because of the spoons in the water, that heat will transfer up the metal or into the handle of the pot. So let's see what that looks like. So we can see on the left here, we have particles that start colliding, and it moves downstream. And each time it collides to another particle, we transfer heat, we transfer energy. Next, we have convection. Now, in convection, heat is transferred by movement of fluid, liquids, or gases. When particles of the fluid are heated, they become less dense and rise. The cooler particles drop down and take their place as they're displaced. And then those particles heat up, and ultimately it starts churning. We can see in this representation what that looks like. We can see that as we heat up the particles, they start rising, which drags the other ones down as they're displaced. And soon we're churning and boiling, and the entire pot is full. Finally, we have radiant heat. Radiant heat is a process of heat energy being transferred from one matter to another without direct contact between the two bodies. The heat is transferred through empty space, through electromagnetic waves. The hotter matter gets and moves radiant through, emitting radiation through empty space. Visible light is a form of this. And what happens is those waves, when they come into contact with another object, like the sun's rays hitting you as you're outside or heating up the ground, is the waves actually move the particles in the system. We see what that looks like here. So as those waves come through, we see that they move the particles, and that generates that energy and kinetic movement. Now that we have covered how heat is transferred, we need to look at how it's measured and quantified. In HVAC, temperature control is one of the key design elements. We measure the heat transfer in BTU or BTUH. We have British thermal units, which is BTU, and we have tons of refrigerant or torr. System capacities are typically referenced in tons or torr. A British thermal unit, or BTU, is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Ton or torr, 1 ton of refrigerant is equal to the amount of heat energy required to melt 1 short ton or 2,000 pounds of ice per day. This is equivalent to approximately 288,000 BTU. So we can see that when we're talking about BTU versus BTUH, we see that time plays a big part here. So we divide that 280,000 BTU divided by 24 hours a day, 1,200 BTUs per hour. Fun fact, the torr unit of measure became an industry standard in 1903 during the formation of the Ice Machine Builders Association of the U.S. These efforts led to the founding of the American Society of Refrigerating Engineers, and this was the predecessor to ASHRAE. Now, heat transfer through air systems. In air, we're looking at 3 classification types of heat transfer. The heat transfer is measured in BTUH and can be represented by 2 processes of energy transfer, or the combination of both. There's sensible heat, there's latent heat, and there's total heat. It's enthalpy. Now, total heat is the combination of sensible and latent heat. Sensible heat transfer refers to heat energy that can be felt or measured. It can be sensed. This is something we would be able to measure with a thermometer. This is measured in BTUH and is referred to as QS. The sensible heat can be calculated with the following formula. Now, Now, you'll see that there's standard and non-standard. Standard represents our standard conditions at sea level. Non-standard would be in higher elevations or different barometric pressures. Now we have latent heat transfer. Latent heat transfer refers to the energy that is used to change the state of a substance. Latent heat cannot be felt. It cannot be sensed. You cannot measure latent heat with a thermometer. Latent heat must be calculated as something sometimes referred to as hidden heat. This is measured again in BTUH and represented by QL. The latent heat calculation is as follows. Again, standard, non-standard air. Total heat transfer refers to the total energy that is transferred during the cooling or heating process. This is measured in BTUH and represented by QT. The total heat calculation of air requires values plotted on the psychrometric chart. The total heat calculation for water can be calculated through measured values because there is no latent heat. It's completely sensible. We're not transitioning from water to ice in the pipe. The heat transfer, the total heat transfer calculation is as follows, and for standard and non-standard air. It can also be calculated by, if you calculate the sensible and the latent and combining them together. If you were to do it both ways, they will be slightly different. All right, heat transfer through hydronic systems. Again, we just talked about, water does not have a change of state as it's going through a coil. This is represented by Q, and the formula is as follows. Now, we just talked about latent heat and the change of state. Matter has four fundamental states of existence: solid, liquid, gas, and plasma. We're not really worried about plasma. For the purposes of this discussion, we will be concentrating on the first three: solids, liquids, and gas. More specifically, what's going on as we transition from one phase to another phase. So let's look at what the phases are. We have the solid state. In the solid state, the molecules are closely packed together, contain very little kinetic energy. They're bonded with hydrogen bonds, and that's what makes them rigid. Ice is an example of a solid state of water. We have the liquid state. Liquid state of matter is nearly incompressible. The molecules are not as closely packed as the solid state, allowing the matter to move and flow and take the shape of whatever container it is in. Example of this would be water. Then we have the gaseous state. The gaseous state of matter differs from a liquid state due to the vast separation of the individual gas particles. As the density of the gas is low, the particles will be displaced and dispersed throughout. This would be fog or boiling water coming off as steam. Now, as we transition between these states, we call that a phase change. And one way to look at it is water freezes at 32 degrees. But it requires 144 BTUs to freeze 1 pound of water at 32 degrees. What does that mean? It means that if I have a glass of water that is 32.01 degrees Fahrenheit, it's still water, it's not ice, and I put it in the fridge and I count to 10, I'm not going to have a solid glass of ice when I open the freezer back up. it's going to take time to freeze and become ice. Now, if we were to put a thermometer and monitor the temperature of water, and we'll say we start at 70, we'll say we start at 80 degrees, and we have a 80-degree glass of water, and we put a thermometer in it, and we stick it in the freezer. We're going, as it sits in the freezer over time, the freezer is going to draw energy out of it, and we're going to see a consistent drop in temperature. And it's going to drop from 80 to 75 to 70. It's going to drop down until we get down to 33 degrees, and then it's going to hit 32 degrees, and then nothing. It's going to stay at 32 degrees. Now, that doesn't mean that energy hasn't continued to work or to be transferred. But now, instead of lowering the kinetic energy of the particles, that energy that's being transferred is actually allowing the bonds, the hydrogen bonds of the chemicals to start forming and bonding those particles together, which is what makes the solid state. So during that transition, we're actually not changing the kinetic energy as we're bonding the particles together. So we're not seeing a temperature change. Now, once we freeze and once we become ice, and there's no more bonds and phase changing to be done, we now start seeing the temperature start going down again. Now it's 31, 30, it drops. But during that transitional period, we don't see the change because the hidden heat or latent heat is what's being used. So let's look at what phase changes look like. So we're going to say that this is a system. This is ice, and this is ice, and we see that all the particles are in line and uniform and bonded together, and there's very little movement. As we apply heat, we start seeing more and more that those bonds are starting to break apart, and the particles are moving. Now, this is what a phase change is. We're moving into now a liquid state. So those bonds are no longer holding them in a rigid configuration. Now, as we apply even more heat, we can start seeing that they get more agitated, they start breaking apart, and we're going to start seeing particles actually breaking off and going off into and they're no longer held together at all. They're going to start going into the general atmosphere. This would be a gaseous state. This is evaporation. So we can see. Okay. Now, matter will change from one state to another state based on the transfer of heat energy. The pressure also plays a big role. This is why water will boil at different temperatures depending on the altitude. Pressure is why we have standard and non-standard conditions. Let's look now that we've seen that the change of state. It's time to talk about relative humidity. Now, relative humidity is a term we hear a lot, and it's something we measure. Let's understand what that means. We know that air contains moisture, and air can be thought of as a sponge. And depending on how that sponge is compressed or decompressed, it's going to hold more, or it's going to be able to hold more or less water. So when we look at relative humidity, we have to imagine that we have three exact samples of air, right? We have three pounds of air that we're looking at. They're the exact same, 70 degrees, with 88 grains of moisture, with the capability of holding 110. That's 80% relative humidity, and they're all 13.62 cubic feet. Now, we take number two, and we're going to say, let's heat it up. We're going to heat that that pound of air up to 90 degrees. What happens? Well, you heat it up, it expands. Now it has 88 grains of moisture still because we didn't take away your add, but it can hold 217, which means that it's now 41.6% of relative humidity, and it's now 14.14 cubic feet. So if we look at sample number 3, and we go the other way, we're going to say, let's cool this pound of water down, or pound of air down. We're going to go to 50 degrees. What happens? Well, we actually condense and we squeeze the sponge, but we've squeezed it to the point where it can't hold 88 grains of moisture. So it pushes that moisture out. It can hold 53. It has 53. So where does the rest of that go? It condensates. Okay, so let's clarify and maybe give a little practical look at what we just covered. So we started out with 1 pound of air represented by this cube, where the pound of air was 13.62 cubic feet, but we're just going to pretend. This represents 1 pound of air at 70 degrees, holding 88 grains of moisture with the capability of 110 grains of moisture. Now, that means that this is 80% at capacity. So it's 80% relative humidity. Now, in the example we just showed, what happened was we took this the same exact condition, and we applied heat to it. We raised this from 70 degrees to 90 degrees. So the 1 pound of air expanded. It's still 1 pound of air, but it expanded and has the same amount of grains of moisture in it. Now, you can see that because it's bigger, it can hold more. So our relative humidity dropped down because it's only holding 41.6% of what it can hold. So it can hold 217 grains, but we're only at 88 grains. Now, in our third example, we took our starting air condition, and we cooled it down. So what happened when we cooled it down was compressed, and it went down. And now in this condition, this pound of air can only hold 53 grains of moisture rather than the 88 grains of moisture. So if it can only hold 53, it was like squeezing a sponge, and those other grains of moisture had to come out. They had to fall out and ended up as condensation. And those grains of moisture, as they're wrung out of the air through like a cooling coil, they gather on the cooling coil, and that's what forms the droplets of water, and ultimately why we have condensation lines. 1 grain of moisture equals 6.5 droplets of water. 1 grain of moisture is 1/7,000th of a pound of water. 1 pound of water is 7,000 grains of moisture. 8.34 pounds of water is 1 gallon of H2O. Knowing this, we can calculate how much water is being drawn out or added into a system at any time. Okay, now that we have an understanding of heat transfer, humidity, condensation, let's run through some basic formulas to calculate heat transfer. We're going to imagine a system, an air handling system, and we're moving air through a cooling coil, a chilled water cooling coil to be precise. So we have air that's going to be entering the coil. That's going to be your mixed air. And you have the air that's going to be leaving your coil, going to be supply air. So we've measured the conditions. I've already plotted everything on the psychometric chart. Again, we're not getting the psychometrics today. But we've plotted the key points that we need to run the formulas to calculate sensible, latent, and total heat transfer. So we know how much flow we have going in. We know the dry bulb and wet bulb temperatures on the entering and the leaving. We know how many grains of moisture we have entering, how many grains of moisture we have leaving. And that's grains of moisture per pound of dry air. And we know the enthalpy of our entering and leaving air. So first thing we need to do is we need to calculate the differential. Now we have our maximum, or we have our mixed air, we have our supply air. We calculate the difference between the temperatures, that's the differential, the grains of moisture, and the enthalpy. Now, the CFM, that remains the same, it goes in the coil, comes out. So now that we have this information, we can use it to calculate our sensible, latent, and total heat flow. And we had these problems or the formulas were shown earlier, but we'll show them again here. So this is the formula for calculating sensible heat. Pretty straightforward, and it can be measured without psychometrics. So I'm going to give everybody a minute here, and let's see if we can run this calculation and see if we can do what answer you get. Okay, so this is how your formula should have looked based on the information we had. We take our CFM times our differential in dry bulb times 1.08. This is all standard. That gives us 115,540.02 BTUH. So we've calculated our sensible. Now let's take a look at calculating our latent heat. Similar formula, but we have our constant, we have our CFM, and we have our differential grains of moisture. So again, I'll give everybody a minute and see what we all come up with. Okay, so again, this is what we should, and our formula should look like. When we calculate that all out, we should get 32,221.46 BTUH. Okay, let's calculate our latent heat transfer. Now again, formula there, we have our constant times our CFM times our differential in H. Okay, so this is what the formula should look like. 4.5 times 4,885 times 6.86. That gives us 158,799.95 BTU. So now we can check our work. As I said earlier, we have we can calculate total BTUs through the formula we just ran, which is the differential in enthalpy. We also should be able to add our sensible and latent calculations together and come up with roughly the same number. Now, they're not going to be exact because we're dealing with, if and decimal points when we're trying to add two formulas together versus running the enthalpy formula. But we should be within a couple percent. So we can see here that when we plotted it and did our differential age, we had 150,799.95. And when we add our sensible and latent, our total is 147,761.48. So we're within 2% when we compare those two numbers. So I'd say we did a pretty good on that one. So bonus question, problem number 4. Based on that, what's our GPM? Now we can calculate our GPM, but we have to rearrange the formula that we went over earlier. So we had BTUH equals 500 times GPM times the temperature split. Now, we know the BTUH because it's the total, but we don't know the GPM. So we have to rearrange that formula just a bit. And so that formula is going to look like this. You can see this formula here. This is what's going to be rearranged to. So let's see what we look like and run this formula. We have everybody met. Okay, the formula should look like this. And if you run through that formula, your GPM should be 29. All right. Now we've gone through and covered the basics of heat transfer. We've defined energy, temperature, and heat. We've looked at how to calculate and quantify the flow through air and water. We've defined sensible, latent, and total heat transfer. So I think we've covered most of what we want to cover. Obviously, there's a lot more to this topic, and this is kind of a precursor into psychometrics, which definitely deserves its own webinar. But I hope this was helpful. And with that, do we have any questions?
Thank you so much, Justin. We can definitely go ahead and hop into the Q&A session. Just a quick reminder to everyone, if you have any questions for Justin, please go ahead and click on the Q&A button and share the questions along. Justin, I can see that we have the first question here by Mike, and he says, hello, I believe latent energy was described as can't be felt. I thought it could be felt as moisture or the muggy feeling outside on a humid day. That's what his question is.
So Can everybody hear me?
Yes, I can
Okay.
hear you.
So yeah, so the question was, why can't you feel latent energy? So latent energy, we feel sensible energy because we actually feel the kinetic energy difference. Latent energy, as we call hidden heat, and it's described as not being, you can't feel it. But on a human's natural method of cooling is sweat. And so on hot days, when we sweat, we sweat, and that evaporation pulls energy as it evaporates. And ultimately, as that energy is pulled out through the latent heat process, um, it ultimately translates into what we experience as a cooling effect. Because our body is continuously trying to cool and push more moisture out to get rid of that total energy. Remember, we have total energy, which is kinetic, and so we have our sensible and our latent. So um, as we pull latent energy off of us through sweat and moisture, we can certainly have a sensation of cooling as the sensible heat transfer is coming out of our skin as it's replacing that energy that was pulled out through the latent. This is why in extremely humid weather, you can't cool down because you can't evaporate that moisture. So it is a little confusing because when you say, oh, well, you can't feel it, but ultimately it's kind of like the same as standing under a ceiling fan. The ceiling fan is moving air across you that's the same temperature in the room. It's not conditioned to air, but what it's doing is it's moving air across you like an evaporative coil, and it's pulling that latent heat energy out. Hopefully that answers your question. Sam, do we have any other questions?
Oh, looks like I was on mute. Thank you so much, Justin. The next question was by Alok, and he said, when we see the delta T at the coil much lower than 10 degrees Fahrenheit, chiller design, what would be a solution to the problem?
So when we see the water temperature through a coil, so it's going to depend on what the coil is, what the intent of the activity is. Are we trying to dehumidify? Are we trying to just cool? There's definitely a difference in how those coils are going to be designed and used. But typically, when we start seeing a higher temperature split, it's typically because we're moving on the water side. If we're moving air too slowly through the coil. So it's kind of like if you were to walk through a freezer warehouse. If you walk through it and you just enter and you walk all the way through, you're going to cool down, and when you exit, you're going to be a little bit cooler. If you run through as fast as you can, you might feel a little cooler, but it's not going to take all that energy. If you stop halfway through and look down at your phone and start playing a game and stop moving, you're going to freeze. So coils are designed for not only the specific amount of flow, whether it's a heating coil or a cooling coil of water or refrigerant, it's also designed to have a specific amount of air moving across that coil. So when they move too slow and you start getting like on a DX coil, if it moves too slow, it'll actually wring the moisture out to a point where it starts freezing the coil, and those droplets of water build up so much that they start freezing and you turn to a block of ice. Now with chilled water, you just wring it out more and more, and that's why chilled water is really good for dehumidification. Typically, the coils are a little wider and give a little more surface area of those fins. But ultimately, if you're not getting the split that you should be getting, your flow on either your water or your air is probably not correct.
Thanks again, Justin. To move on to the next question, this one says, is there a way to better control humidity in hospital pharmacies or operating room that require colder space temperatures?
So this is kind of an ongoing issue. So ultimately, as we get lower and lower temperatures, humidity control becomes a lot trickier. Because when we talked earlier in the presentation about air acting as a sponge, if you stick a sponge into a bucket of water and you get moisture out and you pull it out and squeeze it into the sink and you dump out water, if you keep your hand closed and don't allow that sponge to open back up, if you dip it back in the water, it's not going to pick up much moisture. Well, the same is true for air. So when air is, a lot of people think if you just turn the temperature down, we'll bring out the moisture and we'll dehumidify. Well, if you bring it down without a proper humidity control scenario, you're going to get cold, humid air. And the reason that is the air comes in, it picks up moisture, it goes through the cooling coil, and the cooling coil condenses the air, it wrings the moisture out. But at a certain point, the room gets so cold that the air can't expand and cannot accept any more moisture. This is where desiccant wheels come into play to kind of artificially simulate that. Reheat coils, so there's time to where we can super cool to wring out even more moisture. We super cool and then run it back through a reheat coil. But again, this is going to require, a certain amount of discharge air temperature to allow continued moisture retrieval. The other issue that we run into is adjoining spaces. Now, for clean rooms and hospitals, a lot of times the rooms are positively pressurized. So we have pressure moving out of the room. However, vapor pressure, and this is going to get more into the psychometrics, but ultimately air can be moving in one direction out of the room while moisture is still being drawn into the room. So one thing to take consideration of is the adjoining spaces. It's kind of like if you were to have water spilled on one side of the door, and on the dry side, you start shoving a paper towels under the door, you may moving the paper towels into that other space, but that moisture might start seeping in faster than you're pushing those in. Same thing happens with moisture. As we talked about, everything's looking to get to a neutral, natural state, whether that's energy, whether that's moisture content, everything's trying to get to a state. So if we have a high pressure, whether that be air pressure or vapor pressure, and it's in contact with a low pressure, it's going to try to equalize that pressure. And the high pressure is going to push pressure into the low pressure.
Thank you so much, Justin. Brandon says, great job, Justin. And just a quick reminder, everyone, we still have a couple of more minutes remaining. So if there's any questions that you have on your mind, please go ahead and use the Q&A button to share them in. Justin, I'm going to use one of the sample questions that we had. I'm not quite sure if we've already addressed it, but the question was, how does equilibrium come into play when water leaving a cooling coil is not the same temperature as the air leaving the coil?
Okay, so this is a good one in the sense of, so we talked a little bit about heat flow versus heat transfer. And so when you have a hot rock and it's been hot because it's sitting in the sun all day, and you were to put it into a pot of water, ultimately you have cooler water, hotter rock, and that energy, the higher energy of the rock is going to transfer into the cooler energy of the pot of water, and ultimately they're going to become the same temperature after they reach that equilibrium. Now with a cooling coil and a pot on the stove, ultimately we are, I don't want to say artificially, but we're forcing a continuous flow of heat energy. It's not a hot system and a cold system just coming together and equalizing. We are either continuously drawing out, or we're continuously adding energy into another system. So the reason we don't see that is if we turn the water off and we weren't flowing through the coil, eventually the cooling coil water would be the same temperature as the air passing in, because there wouldn't really be, at a certain point, they just equalize. But because we're continuously forcing either hot or cold water through that, and we're replacing that water, we don't reach equilibrium. It's trying, but it's not going to.
That's great. Thank you so much, Justin. And I think with that, I don't see any questions that have come in. I'm just going to give it a quick second. Yep. I think we can definitely move on to the last slide. Thank you so much, Justin. With that, that's a wrap for today's webinar. Thank you again, Justin, for an excellent presentation and discussion. And thanks again to our sponsor, Evergreen Telemetry. Attendees, sure. Let's keep the momentum going by joining us next week for the AABC Eastern Regional TAP Seminar in Baltimore, an in-person opportunity to dive deeper into testing and balancing with top industry experts on March 25th. And the next thing that we have is, don't forget to mark your calendars for the AABC Virtual TAP Technology Showcase on April 8th, 2025, where you can explore latest innovations in TAP technology for free. So you can hop on, you can learn the possible solutions that can be used for your company, for your work, and everything is for free. So just make sure that you go ahead and scan that and register for that upcoming showcase. And again, thank you so much, everyone. Thank you, Justin. You guys have a great day. Goodbye.